In the previous screencast, I showed you how we can use something known as the matrix approach to multilinear regression to determine model parameters. In this screencast, I'm going to build upon that previous one, and I'm going to show you how we can analyze statistical properties of least squared estimators. In particular, the standard errors of those coefficients in our multilinear regression model. So recall, we have our model here, our multilinear regression model. This can be written in matrix form as follows, where we have our vector of observations, our inputs that go into the model matrix. These are our experimentally collected data. It's really important that you're adding in a column of all ones at the very beginning of your X matrix. And then we have your model parameter vector and random errors. And using minimization of least squares, we can calculate a beta hat. This is an estimate for our beta vector, the coefficients in our multilinear regression model, that minimizes the least squares. Now what we're going to do is we're going to calculate statistical properties of the least squares estimators. The fitted model in matrix form would be y hat, this is our model prediction, is equal to our observations, our X array, multiplied by our estimate for the coefficient vector. The residuals are always the difference between our observations, that's y, minus our predictions, which is y hat. There's a distinction here between y hat, that's our model prediction, and our observations, which is y. We can calculate something known as sigma hat squared. Sigma hat is also known as the standard error, by calculating the sum squared of the residuals, also known as SSE, and then we divide by n minus p. N is the number of observations, p is the number of parameters in our model. And again, p is equal to k, the number of regressor variables, plus 1. By the way, just as a reminder, sigma hat squared is an estimate for the error term in our model. So we have this epsilon at the very end. Epsilon is different for every observation. And sigma hat squared is an estimate for that error term. In order to determine the standard errors of the least squares estimators, we first must determine this matrix known as C. C is equivalent to XTX inverse that we've previously calculated in that previous screencast. This is going to be a square matrix, a K by K square matrix. The diagonals of this C matrix are very important. So these items are really important. They're related to the variances of our least squares estimators. Once we have C, we can determine the covariance matrix by multiplying C by the estimate for the error variance, that's sigma hat squared. So our covariance matrix is just simply sigma hat squared multiplied by this C array. The covariance matrix is also a K by K square matrix. Once we have C, we can extract the diagonal components to determine the standard error of any single estimator. So the standard error of the jth element of our beta hat vector is just the square root of sigma hat squared times Cjj. And I'll show you how to do this in an example in a few minutes. So we're going to revisit our example from the previous screencast. We have a bunch of data here for the satisfaction of hospital visits. We have 25 observations here, and we're trying to create this simple multilinear regression model. So we're continuing from the spreadsheet that I created in that previous screencast. We've created our beta vector, and really this is beta hat. These are our estimators for our multilinear regression model. What we're trying to do is calculate the standard errors on each of these coefficients. In order to do that, let's kind of work backwards. We first need to calculate sigma hat squared, which again, sigma hat is known as the standard error. We also need to calculate this C array. C, we've already calculated. C is equivalent to XTX INV. So this here, XTX INV, is the same as C, our C array that we need. In order to calculate sigma hat squared, that's SSE over n minus p. SSE also is just a sum squared of the residuals. So what we're going to do is we're going to calculate our residuals, the difference between the observations and the predictions. Then we divide that by n minus p. We substitute that into the standard error, and we extract the diagonal components of this C array. So I'm going to add a couple of columns here. I'm going to add 3 columns here. we first need to calculate our prediction, and this is y hat. That's our model prediction. Once we have the model prediction, we're going to calculate our residuals. That's the same thing as E over here. I'm going to first go over here and name our beta hat array. I'm just going to name that beta. In order to calculate our model predictions, all we have to do is take x multiplied by beta hat. So I can just do mmult of x times beta, press enter, and these are our model predictions. You notice that the regression output, if I click over here, the regression output provides the predicted, and so we can just check to make sure that we have the same thing, which we do. I'm going to go ahead and name this, Control-Shift-Down. I'm going to name this vector y hat, and now I can calculate the residuals as y minus y hat. Press enter, and these are the residuals. Once we have the residuals, I can calculate SSE, the sum squared of the residuals. Let's first go ahead and name our residuals, RES for residuals, and the sum squared is simply sum squared of our residual vector, which is 101,039. We're also going to need to know what n is. N is the count of y, for example. We're also going to need to know parameters. This is the number of parameters in our model. I'm just going to put in 5 because there are 5 parameters, beta naught through beta 4. We are ready to calculate sigma hat. Sigma hat is also known as standard error. Standard error, going by this formula up here. Before we can calculate standard error though, let's go ahead and name all these things, including standard error. I can go to the Formulas tab, Create from Selection, click OK. Standard error, or sigma hat, is the square root of SSE divided by n minus p, and we get a standard error of 7.21. We can check to make sure that both of these are the same as the regression output, SSE and standard error, 1039 and 7.2. So let's go to the regression output. Standard error is 7.2. Sum squared of the error, SSE, that's also known as the residual sum squared, is 1039. Now that we have sigma hat, again, that's the same as SE, I'm ready to calculate the standard errors on our regression coefficients. And I'm just going to put that up here, SE of beta. This is just a label. So right here, I'm going to have the standard errors of our coefficients. This first one is beta naught. That's just the square root of SE, our standard error squared, times, we multiply this by the 0, 0 component of C. And so that's down here in this first element. That's our first diagonal component. And when we press enter, we get a standard error for beta naught of about 6.04. Now I'm going to do the same thing. I can just drag this down, but I'm going to change that diagonal component to either the 1, 1, the 2, 2, the 3, 3, or the 4, 4 position. So all those diagonal components. And we end up with the following standard errors for our regression coefficients. We can compare those. So the first one is about 6, the last one's about 1.1 to what the regression output gives us. The regression output gives us the standard error of those various coefficients. In the next screencast, I'm going to show you how we can perform hypothesis tests. We can determine if these coefficients are significant or not. And we're also going to determine confidence intervals on the coefficients. And in some subsequent screencasts, you're going to learn how to create confidence intervals on the mean response and prediction intervals on future observations, similar to what we did using simple linear regression. Thanks for watching.